All right, ladies and gentlemen, this class recording has started in English. If you don't get that joke, sorry. Okay, section 4.2, like it says here in the title, adding and subtracting vectors. If we look at the first picture on your packet, which is right at the top of the packet titled 4.2, but it also comes from page 121 of your book, there is a very simple treasure map made by, two kids in the backyard, right? So we start at the sycamore tree, because where else would you start? Right? Somebody this morning commented that made this sound like a Disney adventure. Yeah. Anyway, 5 paces to the north, 3 paces to the east, start digging and you'll find the treasure. First question, distance traveled for this trip would be what? 8 paces. Distance traveled being a scalar, regardless of what direction we're going, we just keep adding up the distances and we go along. Displacement for this trip, Luke, is represented by which vector on that picture? C, or the purple one, right? Because it goes straight from where we started to where we finished, without regard to which way that we're going, okay? That vector, the purple one in the picture, is labeled as the net displacement, but more importantly to our discussion here, if you look at the top right-hand corner of your page, of your packet, you have one vocabulary word for this section, and that is resultant. Okay? That purple vector is the resultant vector of vectors labeled A and B in that picture, because the resultant vector represents the sum of 2 or more vector quantities. The resultant vector represents the sum of 2 or more vector quantities. Okay. Meaning, if we're talking about trips, like walking trips, the resultant vector would represent our displacement, because it's a straight line from where we start to where we finish, which represents what we call the vector sum of those vectors. Okay? Good there. All right. Now, in the last section, 4.1, we talked about ways to find that resultant vector. These 2 vectors to begin with, A and B, just happen to be perpendicular to one another, right? One's north, one's east, right? So finding the resultant vector here is just doing what? Finding C. And how do we do that in a case where we have a vector to the north and a vector to the east? If they're perpendicular, finding C would involve using what? Pythagorean theorem to find the magnitude, right? And then we could use any of our trig identities to figure out the direction, solving for an angle within that triangle, etc., etc., etc. Okay? Good there. All right. However, the resultant vector is still the vector that represents the sum, even if the 2 vectors aren't perpendicular to one another. For example, if you go to page 2 of your packet, right up at the top, figure 4.12, we have a vector A, and we have a vector B, and then we have a vector C as well. C is representing, or C is the resultant of A and B, because it's a straight line from where we start to where we finish. Good? Okay. Now, that doesn't change the concept, But can we use Pythagorean theorem on this triangle? No, because it's not a right triangle. But that doesn't change the fact that C is the resultant of A and B. Okay? Good there? All right. First key point that sort of merges those two things together shows up on page 1 of your packet. And it says, to add two vectors, A and B, place the tail of B at the head of A. The sum, which is labeled as C, is the vector that extends from the tail of A to the head of B. So we line them up in order. If we go back to this, simple treasure map here, in a treasure map that kind of makes sense, right? We do one part of the map first, then we do the next step, then we do the next step, then we do the next step. These vectors are lined up head to tail. B starts where A ends. Okay? Good there? The vectors at the top of page 2, figure 4.12, picture A, these are also lined up head to tail. B starts where A ends. It just so happens that they're not perpendicular. Okay? Good there. So first, we have to make sure our vectors are lined up properly. Okay? To illustrate that point, right in the middle of page 2 is conceptual example 4.5. So conceptual example 4.5 says, which is the vector sum? Another way that we could ask that question is, which is the resultant vector? Because those two things are synonymous. Come on. There we go. So this, another way of saying that, is also which one is the resultant vector. Okay? All right, so it says consider the vectors A and B shown to the right. Which of the other four vectors in the figure, C, D, E, or F, is the sum of A plus B? Okay? It's C, right? So, Brett, to get there, first, we said, how do we have to line our vectors up in order for us to figure out the result? The tail of B has to start at the head of A, right? So, if we go, I'm sorry, keep this out of the way. Move this down here. If we go, let's say we call this, not what I wanted to do. So full disclosure, right? This is my first day using this program with the arrows, which is really important in this chapter, but we haven't really come across it yet. So I'm basically figuring out the program as we go along. So if I mess up, bear with me. Right? If you're on the recording, sorry, fast forward this part or something, I don't know. All right, so here, I don't want a dotted arrow. I want a solid arrow. All right, so we'll draw this right here, and this will represent vector A, okay? And then I'll change colors, and we'll make this one here vector B, okay? So we have to line up A and B properly before we add them together, okay? Right now, B doesn't start at the end of A, but that's all right. On page 2 of your packet, next to figure 4.12, just above conceptual example 4.5, it makes the point that vectors are unchanged if we move them to other locations. In figure 4.10, 4.10, this has several vector A's that are drawn. every single one of those vectors is exactly the same. Because, why? Length of those vectors is the same, meaning they have the same magnitude, and they all point in the same direction. Even though they're in different locations on the picture, they're all still pointing in the same direction. Every single one of these vectors is vector A, regardless of where it shows up on the xy axis. So, in a situation like this, where we're trying to figure out the vector sum of A and B, but they're not drawn in a proper orientation, we can fix that. We can just move whatever we need to move from one place to another. Like this. Okay? Good there. And then we said the resultant vector, or the vector sum, is the vector that's drawn from the beginning of the first one to the end of the last one. Right? And so that would go here, here, and just like that. Right? That's the one that starts at the beginning of the first one and goes to the end of the last one. And that would match the magnitude and direction of which vector in that diamond? Vector C. Okay? Brett, go ahead. Hold on 1 second to that question. Hold on to that question just for a second. Yep. Good here. Good so far? Okay. Another thing to keep in mind. Do I want to do that now? Yeah, we'll do that now. This is A plus B, because B starts where A ends. But do we have to add them in any specific order? Does the answer to a scalar addition problem, if we go 3 plus 4, is that any different than 4 plus 3? Same answer. Has to be the case with vectors as well. So even if we had taken B first and then started A at the end of B, the resultant still goes from the beginning of the first one to the end of the last one. It's just, in this case, it starts in the red and goes to the end of the blue, and we still end up with the same answer. Okay? Good there. Yes, no, maybe? Okay. This is conceptual, right, Brett? We haven't put any numbers on this picture yet, and that's okay. We're going to get there, but we got to get this conceptual stuff first. Okay? Good there. All right. If we go back to the packet, page 1 of the packet, figure 4.9, down at the bottom of the first page of the packet, okay, has a much more complex treasure map. Wow. Okay. We have added a third segment of the treasure map. So first, 5 paces north, then 3 paces east, but then 4 paces southeast. Distance traveled for that trip would be what? 12 paces, because distance traveled being a scalar, we just keep adding things up as we go along. Okay? But the displacement is represented by the purple arrow, which again, in this case, is a resultant vector, because it starts at the beginning of the first one and goes to the end of the last one. That purple vector, like it says right here, represents vector A plus vector B plus vector C. So we draw it from the beginning of A to the end of C. And it says, key point, right? To add more than 2 vectors, first place all of the vectors head to tail, and so on. Then draw the resultant vector from the tail of the first vector to the head of the last vector. So we don't change the process, just how many steps are in that process. Okay? Good there. Again though, well, here we run into a problem that we didn't have up here, right? What shape did this resultant vector and the two other vectors make? Right triangle. We can use Pythagorean theorem, we can use trig identities, all that stuff. Here, not so much, right? That's not a right triangle. We can't use Pythagorean theorem on it, right? At the top of page 2, figure 4.12, picture A. That's not a right triangle either. It's a triangle, but it's not a right triangle. So Pythagorean theorem and trig identities came in handy when we had the vectors lined up perpendicular, but when they're not perpendicular, it's not as obvious as what we do. Okay? Good there. All right. Just one point, then we'll get into the nitty-gritty of this. All right. That's right. Nitty-gritty. Luke didn't even notice. All right. Just one last point here, right? So here is our extremely complex 3-step treasure map, right? And if we go this one, vector A, this one, vector B, and we'll go green for this one. This one, vector C, okay? Right now, the arrangement of those vectors is representing A plus B plus C, because A comes first, B starts where A ends, C starts where B ends. But do we have to add them in that order? No. 3 plus 4 plus 5 shouldn't be any different than 5 plus 4 plus 3, or 3 plus 5 plus 4. Regardless of what order we add them in, we should get the same answer. So let's say we did this one first, this one, the second one has to start where the first one ends, right? Just like that. Then the third one has to start where the second one ends. And look where it gets us to. Same spot, right? That has to be the case regardless of what order we arrange our vectors in. They should give us the same resultant vector. Okay. Good there. Okay. Simran, go ahead. Yep. Yes. Sure. Yep. Okay. Yes. Now, remember though, keep in mind what these things tell us, okay? This purple arrow right here represents the displacement if we were talking about walking 2 trips, right? Or, so I mean, if we go back to this treasure map, this might help, right? If we go back to this treasure map, that purple arrow represents the displacement of our trip, okay? Remember, displacement is how far away from your starting point do you end up, okay? It gets you to the treasure on this map because what does the treasure map first have to specify? Where you start. But if I took this arrow, started it at the doghouse, and then went here, and then went here, okay? That is still the resultant of those 3 vectors. And it still gives you the displacement. But you don't end up in the same spot because you didn't start in the same spot, right? So here, remember we said these 2 vectors are the same, even though they're not on the same space in the drawing, because they're the same magnitude in the same direction. Okay, so we introduce it in terms of like this treasure map because it's easy to kind of think of walking from here to there and everything. But remember that displacement really only tells you the difference between where you started and where you finished. If you don't know exactly where you started, displacement can't really tell you where you finished. Does that make sense? Right? On a treasure map, it does because you know where to start. But these two displacements, this one and then this one, are exactly the same displacement, but you don't end up in the same spot because displacement is just a difference between where you start and where you finish, right? Without a specified starting point, we really know where you finish. Yep. The displacement will be the same. That doesn't necessarily mean you would end up where the treasure was, right? Because that depends on where you start. But yeah, both of those displacements are the same, but like I said, that doesn't necessarily mean you end up where the treasure is, because that depends on where you start from. Right, you can move them, yeah, just like this. If it said, you know, regardless of what order you walked them in, you should get to the same spot, as long as you started in the same spot. Right? That was the point of moving these, right? You know, if we move them in a different order, we still get to the same spot. So the treasure map, you know, if we use the treasure map analogy, right, is really only important to give us the starting point. Because after that, we could do the directions in any order, and we would get to the same place. Okay. All right, good there. Okay. Now, how do we figure out that purple line? That's where we ultimately need to get to. Okay? Perhaps you remember this. Yes? Okay. Mr. Toad's Wild Ride, right? Yeah. And let me get Mr. Toad's Wild Ride here. Load up Mr. Toad's Wild Ride. And, okay, that's good. Even though I cut off the bottom of it, that'll be okay. Perhaps you remember from Mr. Toad's Wild Ride that the first trip that we went on started at home and took us to the newspaper. Yes? And I believe, if I remember correctly, that trip was 12.5 miles. One, because it told you that in the directions, but then we had a ruler to help us measure that 12.5 miles, right? And the ruler measured in miles, and we drew it there, and blah, 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 blah. Okay? Right? And then trip 2 took us from the newspaper down to the florist. Okay? And if I remember correctly on that one, anybody remember how long that one was? Hold on a second. I have Mr. Toad's Wild Ride here that hasn't been graded yet. So, there. 12 miles. So this one here was 12 miles. Okay? Good there. Distance traveled for that trip would be 24.5 miles, which seems like a lot of driving to go get a newspaper and some flowers, but whatever. Okay? Part of Mr. Toad's Wild Ride then asked you to do this. To go straight from there to there. Okay? We now know that that purple vector is called the what? The resultant vector. Red and blue are lined up properly, head to tail. Purple goes from the beginning of red to the end of blue. That's a resultant vector. And you figured out, I believe, that resultant vector was 17.5 miles. Right? and you used your protractor and you got the angle and everything was great. So we figured out how long the resultant displacement was. That was easy here on this map. Why? Well, it's a triangle, but is it a right triangle? Because you didn't use Pythagorean theorem to find that resultant vector, right? You had a ruler, right? And all of the lines that you drew on this map, you drew to scale, right? If it was 12.5 miles, you used the ruler to measure 12.5 miles. If it was 12 miles, you used 12 miles, right? There, there, there. Boom, okay? That's one way that we can determine the value of the resultant vector. Bottom of page, bottom of page 2 of your packet. Vectors can be added graphically. Okay? The only problem with adding vectors graphically is you have to draw every single vector that you make exactly to scale. Remember, the length of the arrow is supposed to represent the magnitude of that vector. If you're going to do this graphically, like we did on Mr. Toad's Wild Ride, you got to draw all of your vectors exactly to scale. Because if you don't, you won't be able to measure properly and it won't give you the right distance. Or the other thing that maybe is even more difficult, and I know this because I watched all of you do the lab, right? Not only do you have to make the line exactly as long as it should be, but if it tells you that vector A is 60 degrees above the positive x-axis, you have to draw it exactly 60 degrees above the positive x-axis. Yeah, it's totally a pain in the butt, right? And the big, like, watching all of you guys do the lab, right? If your protractor isn't exactly perpendicular to the paper, right, or exactly flat across the paper, you don't measure that 60 degrees all the same. So you guys all don't get the same answer for this displacement, not really through any fault of your own, just because you have, in order for all of you to get exactly 17.5, you would all have to measure everything exactly the same. Okay? That's hard. Okay? But there is a way that is a little bit more convenient for us to do on an everyday sort of basis. And that allows us to make use of stuff that we learned back in section 4.1. Vectors can be added with components. Okay? So here's what I'm going to do. I'm going to take this picture, and you guys have this picture in your packet. Do this. Bring it here. Okay. So you have this picture in your packet right up at the top of page 3. Okay. You actually have the result of this picture also right next to it, but I'm going to show you how they got there. Okay. Here is vector A. And here is vector B. And here is the resultant of A plus B. Okay? Good. All right. And if everything's drawn to scale, great. We measure that line. It's all good. But if we don't draw it perfectly to scale, there's still a way we can handle it. Okay? It tells us here that vector A has a certain length. And let me check and see real quick what it is. 5 meters. So we know that this vector here is representing a magnitude of 5 meters, and it gave us an angle of 60 degrees. Okay? We learned in the last section that if we know the magnitude of the vector and the direction in which it points, we can actually figure out the components of that vector. Yes? Okay? this is the part that's going to be very difficult. So here we can go. X component here. Y component there. Good? We would find those how? Sine, cosine, right? Find the two sides of that triangle. Okay? Vector B represents a length of 4 meters, and it told us that that 4 meters is at a degree of 20 degrees above horizontal. It's not the x-axis, but that line and the x-axis, this line and the x-axis are parallel to one another. So if it's 20 degrees off of the x-axis, it's also 20 degrees off of that line. Good there? Again, we could figure out components. The next component here, a y component here. Again, using trig functions to get there. Okay? Good so far. We've broken both of these vectors up into their component values. We couldn't use Pythagorean theorem on the original triangle because this isn't a right triangle. But if we break everything up into components, components are either along the x-axis or along the y-axis. If we know the two x components of these vectors, and they both point the same direction, what could we do just with those components? In Mr. Toad's Wild Ride, it asked you to measure all the components of each of those individual pieces, yes? Okay? And you filled in this table right here. What did you do with all the x's eventually? Right? You added them all together. Okay? Some of them pointed left and some of them pointed right, so sometimes you had to subtract, but you added them all together. What did you do with the y components? You added them all together. If we add this one and this one, okay, so I can move that like that on the drawing, okay, even though I originally found this component by breaking up this triangle, I can bring it down here because I can move vectors on the drawing however I want to. Okay? I could bring this one from here to here, right? I know these two dotted lines here, and I know these two dotted lines there. Good so far? You see where I'm going with this? Okay. By adding the two x components of those red and blue triangles, not yet, but I should get the x component of C. If I add the y components of the red and blue triangle, I get the y component of C. What do you know about x and y components? How are they arranged in relation to each other? They're perpendicular to each other, meaning this is now a right angle. Now we have C as the hypotenuse of a right triangle. And guess what we can do with it? Pythagorean theorem, sine, cosine, tangent, any of those things. Okay? Tomorrow, we will walk through one example of doing this, okay, as a class. Make sure we know where this came from, that came from. And then I will give you a couple more practice problems to do together. You know, work in small groups so we can practice this, because this is pretty much what section 4.2 is about. Okay? Good job? Okay. There are some, if you look on the calendar for tonight, there are some questions as homework. These are basically conceptual questions. There aren't any calculations there. It's just about arranging vectors properly, head to tail, drawing resultants, blah, 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 blah. Okay? Good? Let me stop the recording, then I'll zoom in. So actually, I can zoom in right now.